All right, guys. Quartic functions. Now, quartic functions are basically similar as a quadratic, but it's like a quadratic polynomial of degree 4. When I'm saying a quadratic, it's not an actual quadratic, it just has the same characteristics of a quadratic and is written in the form of y equals x to the power of 4, right? Now, when I write this down in the extended form, it's quite more longer, but technically I can write down this in a linear factor form, which you will have something like y equals, let's say, x plus 2, x minus 1, x plus 3, x minus, I'm just making it up, right? I'm just saying that could be another way of looking at a quartic with through 4 different linear factors. Now, there is something for us to really meditate on this, and is that a quartic functions has three types of, there are 3 types of quartics. The first one, it has one turning point. The second one has 3 turning points. Yep. And nope, the last one has one turning point. And 1 point of inflection. What's a point of inflection, by the way? What is a stationary point of inflection? Exactly. Is that point where basically at that point, the tangent at that point is what? What's the gradient of the tangent at that point? It's 0, right? And then it changes as well back to positive. So these quartic functions has 3 forms. Either you have one turning point, 3 turning points, and 1 turning point and a point of inflection. And I'm going to show you what that looks like. Now, my first one turning point. So notice that this graph has very similarities of a quadratic, right? It has, what does the quadratic look like? So the quadratic has this shape, right? What is the difference of that in those two? Like, spot the difference. What is it? What can you see? No, I'm talking about the graph. What are you seeing both? Yep. Thank you. The quartic is flatter here, right? It's not completely flat. It just gets flatter and flatter. So basically, it has similar properties. I will have 2 points side to side. There is an axis of symmetry, basically, in x comma x equals 0, right? And it has, again, a turning point. At this point here, the graph will make a turning point. Oh, that's brilliant. Oh, sorry, guys. 1, 7. All right. There you go. So I can have my graph like that it has that turning point. And look at the shape. Look at the write down of my graph. Is y equals ax to the power of 4, where a, again, what do you think that a will do here? What do you think that a will do? It will be a dilation factor, so it will make it either like wider or flatter in terms of what that a value would be. And I can probably rewrite that Quartic function also in this other form. There are different forms that you can write it down, so you can kind of have similarities with that. Now, I'm going to show you this as well. Desmos is a very beautiful app where I can basically just manipulate functions and show you a lot about it. So look at my Quartic functions, please. Everyone, look at the board and look at as I increase the value of a. Look what's happening with the graph. What's happening? Narrower, and if I get values smaller, it gets flatter until it reflects on the x-axis, right? Now, again, this is just one form of this is the simplest form of the Quartic function. It's similar to y equals x squared, right? Now, I'm going to show you something here that is different. Like, what do you think is going to happen if I raise this to the power of 6? What do you think is going to happen? Am I going to have the same graph, similar, or different graph? Very similar, right? Very similar. So even powers, has similar characteristics. But again, what I'm going to start seeing here, this gets flatter and flatter, right? So this is just basically a way that you kind of understand families as well of parabolas, families of no parabola, families of functions that have either odd or even power. So again, this is just the first like idea of what a quartic looks like. Now, quartic gets trickier as I start changing and manipulating all the other factors. Yep. It does touches. Yep. It's not an asymptote that it touches. Yep. Now, I can have another form of it where it looks like a squiggly line, right? It looks like, but now I want you to hold, like, don't panic. I've got 3 turning points, right? Where my turning point is 1, 2, and 3, right? Now, look at the way that is written. Is my first term is a square, which is a repeated term, right? And then the other 2. What are the other 2? There are the x-intercepts. Can we see that? Similar with this, I've got 2 repeated terms, right? Or I can have 4 individual four individual linear factors, where I will have exactly how many x-intercepts? How many x-intercepts would I have here? 4, right? Now, that's what I'm saying. You could have potentially 1 intercept, 4 intercept, 2 or 3 technically. Does that make sense? Depends on how the graph is written. Now, I want you to notice something here, a pattern that, yes, is a sort of style of the parabola, but as I modify these linear factors, I will kind of like change the shape of my parabola. But they all follow the same pattern, guys. Like, it's always looking like this. Does that make sense? Despite of like the change of it, is always like trying to look this kind of like U shape, right? Like I'm saying that in terms of this, it's just like it's been a change on this section, but it's all kind of like that. Now, what I'm saying that is because that is going to impact again my a value to determine how is going to be the shape of my graph. Remember that in cubic functions, we look at above the axis and below the axis. Here, I'm not looking at that. I'm looking at like, well, it's a positive, so it's going to have like that parabolic shape, technically, right? It's positive, it's going to have a parabolic shape. A parabolic. So it's like a smiley face, but now it's making like that sort of like angry look of it, right? Does that make sense? So there is other different forms. And then the last one is having a turning point with 1 point of inflection. Again, my A value is positive, which means that I will have a smiley face. But again, I'm going to have a modification because of these factors. Now, this one is a turning point of inflection because of what? Can you see this? What's the power of this one? What's the power of this factor? It's the power of 3, which what type of function is that technically? It's like a cubic embedded into a linear. Can you see it? So when we have that type of writing in my function, I will have a cubic look. Like it's like this section of it is my cubic. Yep, that is the part of the cubic function, and then the rest is just the complement of it. All right? I know it's a lot, right? But again, this is super important because again, is another way of drawing graphs with a higher power. Now, when you have your test, you will have your book with you, right? You won't have your calculator. You will have only your book. So taking note of all of these, it would help you a lot to know what type of graph you are going to expect. So the expanded form of the quartic is P of x equals ax to the power of 4 plus bx cubed plus cx squared plus dx plus e, right? That is the longest, or like the expanded form, where all of the coefficients are real numbers and a is different than 0. Okay? A must be different than 0 in order to be a quartic function. Otherwise, it's a cubic. Now, I'm going to go very quick with, again, a transformation of this. It's not too crazy, but it's going to really make sense in a second. So, again, the simplest quartic is y equals x to the power of 4. That is how we write it, right? And we say this, that this has similarities to the parabola y equals x squared. Yep. They both concave up. They have a minimum turning point of 0, 0. Yep. And all of the transformations are similar to y equals x squared. Yep. We will have an A factor, which is a dilation factor. We will have a H value, which, what do you think it would be my H value? What do you think a H value would be here? If I'm talking about translation, a horizontal translation. And what do you think would be a K value here? Vertical translation. Right? So if I have a graph here, and this is my, I'm going to try to make it here. It's quite tricky to draw it as well. Right? My quadratic would be more like very similar, right? If I need to write the whole transformation of this, How would I write this down as a turning point? What do you think? What do you think I would write? A x minus h to the power of what? To the power of 4 plus k. You know this, right? This is a quadratic or a quartic in this case that has been shifted h units horizontally and k units vertically with a dilation factor of a. Here has a turning point of h comma k, right? It has, even though that is quite flat, it still has a turning point. If a is more than 0, we have a minimum, right? Which will have a quartic that looks more like this. If a is less than 0, I will have a maximum and my quartic will look more like that. Yes? X equals h is my axis of symmetry. And how many solutions do you think that I would have with this? How many solutions could I have? Sorry? I can have 0 solutions because cutting the x-intercept, right? 1 or 2 solutions. What are the steps to graph this quartic? What are the steps to graph it? There are steps to do, all right? So the first step is factorize the equation. And how do we factorize it? Using any method. Now, because it's a very large power, how will you reduce the power of that? What will you do to reduce it? Sorry? Log division, right? You can use the factor theorem and long division. Yep. So the factor theorem is to find out when the function equals to 0 and then divide the function by that factor and then do it again. Find another factor that is equal to 0 and then do it again. You will find out your y-intercept. You will find out your x-intercepts. And your lastly is draw the graph. Yeah, you have to do it twice. You do it one for, and then you go down to cubic, and do it again when you do it into a quadratic, and then you can solve by a quadratic. Unless you can, you know how to solve a cubic by there are forms to do it, but it's easier just to keep dividing. I know this is a lot, all right, but let's keep going. Yeah. I will teach you in a second. I need to go through this part, but like I will allow time for us. Actually, next class, when is it? Monday? No. Next Wednesday. I will actually show you a video. I'm gonna create myself a video and I show you on it. All right. It's just because we are quite behind and we need to catch up with this. But despite of that, guys, the long division method is the most effective. You need to know it anyways. Sorry? Truncus and hyperbolus. And after that, probability. And after that, pseudocoding. And then exams. So it's a lot coming. Pseudocoding. It's computing. Yeah. Well, it's like an area of computing. All right, guys, let's do this question. Let's see how we go with this question. Graph the following. All right, so we got this. Y equals 1/4 x plus 3 to the power of 4 minus 4. Right, that's the first question. Let's start with this. See how we feel with that one. All right, the first thing first. What type of graph is this? Is this a cubic, quartic, quadratic? It's a quartic, right? It's like, I know we're doing quartics, but I just want to ask. How do I know that it's a quartic? Because of that power of 4, right? Now, what does this plus 3 and minus 4 represent? What are they? Sorry? H and K. So I already know what would be my turning point here. What's the turning point? Negative what? Negative 3, comma. Now, what does that mean? That my turning point has moved negative 3 or 3 places to the left, 4 places down, and I will do the graph, right? Now, what is the shape of the graph according to this turning point form? Is it the one that is sort of like this? No. Is it the one, I'm just going to keep doing things. Is it the one that is like this? No. All right, I don't know. I'm going to go with all of them. It is like a normal quadratic, right? It is like something like that, right? Exactly like a quadratic shape, right? It's just to the power of 4 is flat. Now, what are the kind of like restrictions of this graph? Or what are the like the information? Because it's not, the turning point is not in 0, 0. Is in minus 3, 4. So I need to graph that. So that would be somewhere like this. So 1, 2, 3 minus 3, 1, 2, 3, 4. Here is my turning point, right? Yes. So this is my turning point. Now, is it a concave up, concave down? What is it? Concave? Concave down. That's concave up. This is concave up. Sorry? It's concave up. This is concave down. Concave up, concave down. So it means that I will have how many x-intercepts? 2. Would I have a y-intercept? Would I have a y-intercept? Yes or no? Yes. It has to do something like this, right? And it will cut the x, it will cut the y, which means that I need to solve that. Now, let's solve the x and the y-intercept. So this is where it gets interesting. Let's see if we can remember how to do this. You know how to do this. Please don't feel like you don't know. You do know. How do I find the x-intercepts? Make y 0, right? So that would be 0, 1/4 of x plus 3. How do I solve this? Guys, do not panic. Use algebra. Yes, what I start. Thank you. Move that minus 2 away. Start with what you know, right? What do I do next? The 4, so that would be what? 16. How do I get rid of that 4? Power. Root 4 of that, right? Is so it follows the same thing. We have done this before. What is root 4 of 16? What do you think it is? Plus or minus 2. 2 to the power of 4 is 16, right? So it is. Do you all agree with that so far? What do we do next? Move the 3. So I got 2 solutions, right? When it is plus 2 and when it is negative 2. So I will do 2 minus 3, which is x, and I will do minus 2 plus minus 3, which is x. So for my first one, x is minus 1, and for the other one is minus 5. 2 minus 3 is minus 1. Minus 2 minus 3 is minus 5. Yes? Now I'm talking about x-intercepts. I haven't done the I haven't done the y-intercept. I haven't done it. We're gonna do it. Yeah, yep. You were looking the other thing. Y-intercept. What is my y-intercept? My y-intercept is making my x 0, right? Y equals 1/4 of 0 plus 3, 4 minus 4. Now, here requires a little bit of like calculations. I'm just gonna like step up and do the solution, which is 65 over 4. This is approximately 16.20 something, right? Now, here is where it goes. So my y-intercept is somewhere around here, 16.2 something, right? How do I draw this? What are my x-intercepts? My x-intercepts are in minus 5, 0 and minus 1, 0. So in minus 5 and in minus 1 and somewhere right up there. So it will look something like that. Pay attention. Comes down flat. The drawing is very similar to a quadratic, all right? But there is an area of like widen the whole like space of my x's. Does that make sense? That is like the easiest quartic to draw because it's in the form of turning point. I can see exactly, I can identify my x-intercept by doing this. Most of the time you will solve it like that. But I'm gonna do one that it gets a little bit more tricky. I wanna see if I can do this one. Let's do this one. Actually, before we jump on that one, I'm gonna do this one. All right, let's do this one. P of x. Wait. Any questions on this one? Any questions, guys? So far, okay. Yes, so far, all right. Yes. Let's do another one. P of x. Look at this. Minus 3x minus 1, 4 minus 7. This is my P of x. Now, my question straight away. This is in the form of a normal quadratic, just only being translated. It's like a turning point form, right? So it's not like squiggly line yet. Now, my question, is it concave up or concave down? Down. So I will have a maximum point. You'll agree with that? So is concave down? Right? Now, is concave down? What is my turning point? Turning point? Sorry? What is my turning point? Sorry? Sorry? It is, remember, we always equal this to 0 to find what the x value is. You always equal that to 0, which is positive 1, send the 3 down. Right? Now, let's do a quick sketch of that. So I know exactly what am I kind of like finding. What am I doing with this? So it's 1/3, so somewhere around here. And then minus 7 down. 1, 2, 3, 4, 5, 6, 7. And here is my turning point. And am I concave up or down? Concave down. So technically I'm looking at this way, right? My question, do you need to find out your x-intercept, yes or no? No. Why? Because the graph doesn't touch it. And I'm going to prove you that is not even possible to do. So if I do my x-intercepts, which is y equals 0, you will have this minus, right? Now, how would you solve this? Well, send the minus 7 to the other side. You will end up with a negative 3x minus 1, 4. Take the negative away, so you will end up with minus 7, 3x minus 1, 4. And then here is when the error comes. Can you take root 4 or of a negative number? No, it's the same rule as you cannot do square root of a negative 7, right? It's just not possible. It doesn't exist. So therefore, because this is not possible. Therefore, it's like when we did. There are no solutions here. It's concave down, so there is no way that I can have x-intercepts. But I have a y-intercept, which is what? And I'm going to do it very quick. That will be minus 8 and minus 7, minus 8, and then my graph will look something like this. Again, very similar to a parabola, all right? I'm not too particular. I was like, oh, it's not flat enough. When it's like that, it's quite hard to make it flat. Does that make sense? Awesome. Any more questions so far? Now I'm going to go into the kind of like trickiest part of this, all right? Again, there are different combinations. I'm going to write down here quartic parabola. Now, let's find out, let's look at the quartic expressed as individual linear factors, and then you will realize there are different kind of like solutions that you could see. There are 5 different combinations, all right? So I'm going to write them down again. You could have x minus a, oh, actually, you could have a x minus b, x minus c, x minus d, x minus e. And how many x-intercepts do you have here? 4. So this has 4 linear factors, 4 linear distinct factors. So they're all different, right? And 4 x-intercepts. Now the other combination that you can have is you have ax minus b squared, x minus c, x minus d, right? You will have 1 repeated linear factor and 2 distinct linear factors, right? So you have 1 repeated linear factors. The next one, y equals, again, that coefficient a is always there, x minus b squared, x minus c squared. 2 repeated linear factors. The next one is having now 1 factor of multiplicity of 3, or it's now of a factor of 3, which is x b cubed x c. We call that multiplicity of 3. And then the last one is that you have a x minus b to the power of 4, where this one will have a turning point form. A turning point of this one would be in b comma 0. Okay? Now this is a lot, guys, and again, it's hard to digest all in one go, but again, that is one basically chapter, and technically we can skip kind of like parts of practicing, because again we have done these things together. All right, I'm going to show you using decimals what it looks like when I modify things of the graph. So please everyone just look at the board. So that is my normal quartic in the form of ax4. But look at what happened when I do it in this form, right? Now notice this one. I've got one repeated factor here and two distinct linear factors. Now my repeated factor is ax squared, which is in 0, and this one would be b and c. All right. Now b and c are given by these two values. Right. Now notice what happens when I start modifying things. So this could be the graph, right? And again, at this stage, I don't care how far or how close you go on those turning points, as long as you're doing this shape, right? That's all what matters. And notice my A value is positive, still technically a smiley face shape, right? If it's negative, it just goes down. Look at this. And then the shape is like that. Does that make sense? My A value now is negative, now is concave down, but because B, A, and C are in the equation, I need to account for that. Now, the next one is this one. What happens when it's a double one, right? Oh, no, not that one, not that one, not that one. This one. So that one again, we got the double on this one, x-intercept comes down, and then there's another double here. The other one is 4 distinct x-intercepts, B, C, D, and E, B, C, D, and E. All right, so again, it's the same kind of like shape of my quartic, but now it's affected. So it always has this like up, down, down, up, down, up. It's like a S thing shape. Now, the one that I find that is the trickiest to graph is the one that has a stationary point of inflection, which is this one. Now, I want you to look at as well where my stationary point is, which is in C, which is in 1.3, which is exactly here. Right? So, look at this. This is my point where my graph cuts on B, right? But the other one that is repeated 3 times would be my point of inflection. So whatever value is that is basically the form of a cubic. Does that make sense? Does that make sense? And if I flip that to the other side, let's say, for example, is a negative, right? The graph again is a concave down or side face, and then it comes up here, cut in here, comes down, and then from this point is a cubic function. Can we see it? Yep. There you go. That is basically how you manipulate all of these tools for your benefit, all right? The only way that you get better at visualizing this, again, is by graphing, is by practicing. There is no other way. It's a lot, yes, but this gets like more intense as we progress. And then we're going to see even more intense graph, which are called truncus. and we are going to see another one which is called a hyperbola. Now, those two are not part of year 10, but I've seen the benefit of learning that from now. They are year 11 content. So we need to know those two. So when you step into year 11, you know exactly what you are drawing. It's not a mystery anymore. All right? You have a question? Good question. This is week 2, potentially next week 4. I need to reassess the whole thing because it's different. I will send you an email on that. Yep. Yes. So with this one, basically, you will do one. You run out the factors, also the factor theorem, right? You find out that you end up with a cubic, right? As a factor. Do it again. Find factors from that cubic function that now equal that to 0. And then find the quadratic, and then the quadratic you find your value. Let's do one question like that. It's a bit tedious, but let's do it. Yep. Sorry? Yeah, I'm gonna do a question. Let's do a question, guys, where we have to break down the graph. Um, all right, let's see if we can do this question, guys. Y equals, guys, x4 minus x cubed minus 12x squared minus 4x plus 4. All right? Is a quartic, right? In order for us to find out the solution of this, I need to find out again factor theorem. That is the first step. The factor theorem tells me that I need to find a value that when I substitute it, it will give me a factor, a solution equal to 0, right? So let's start. Let's start, guys. Please look at values 0, 1, 2, minus 1, minus 2, and tell me which one is it. All right? You can do it. You can do this part without me doing it. All right? Factor theorem, which value equal to 0? Totally, I mean, definitely looks like 0 is not. Do it, do it. I need you to do it. Do not wait for me to do it. Yeah. Coming, 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 coming. This question is gonna be ugly. Guys, pause, 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 pause. This question is wasted. It's not. This question doesn't work. So we have the function x, whoop, x4 minus x3, whoop, minus 12x squared plus 4x plus 4. Yep. Did you get that? Guys, you get the same thing? Now, doing this one again, let's find out the x-intercepts on that one. Analysis, G-solve, roots. Sorry? There you go. And notice that the roots are these values, all right? So that's why it's not gonna, we're not gonna be able to do it. Minus 2.69, then minus 0.83, 0.4, and 4.1. Now, again, when this is breaking down into factors, that those would be your solution. Now, I'm not going to give you something like that in your test. I'm going to give you something that it will give you actual whole numbers. All right, I'm not going to be as so mean to give you something. Like, let me try to find one that the solution would be what we're looking for.